Okay, this is chapter 8 homework. It says a laser beam with that wavelength, 632.8 nanometers, is incident on two slits that are 0.2 millimeters apart. How far apart are the bright interference fringes on a screen 5 meters away? So this is the situation that we have. We have a double slit. The distance between the slits is 0.2 millimeters. And then on a screen that is a distance 5 meters away, we have an interference pattern. It's asking me how far apart are the interference fringes. They're actually going to be spaced differently as you go out, but we'll just assume that we're talking about what is the distance between the 0th and the first fringe. So I want to know what is this distance, y. So let's just write down what I know. I'm going to write them in SI units. D is equal to 0.2 times 10 to the minus 3 meters. Lambda is 632.8 times 10 to the minus 9 meters, and L is 5 meters. I want to know what is the angle from the 0th order to the first order. So I want to know what is this angle, theta. All right, and I can say for bright spots in the double slit interference pattern that d sine theta is equal to m lambda. Now this is m equals 0 and this is m equal 1. So I'm going to use m equal 1 because that'll give me the angle to the first order fringe. I'm going to solve this for theta. It is the inverse sine of m lambda over d, which is the inverse sine of 1, 632.8 over d, 0.2, 3 meters, and that gives me an angle of 0.18 degrees. Okay, so now that I know that angle, I can say y is equal to L tan of theta. Notice that I have a triangle here. In this triangle, this is theta, this is L, this is y. So tan of theta is y over L, so y is equal to L tan theta. So that's equal to 5 meters times the tan of 0.18 degrees, which is 0.016 meters, which is 1.6 centimeters. So that's the answer. Okay, in Young's double slit experiment, a set of parallel slits with a separation of 0.1 millimeters is illuminated by light having a wavelength of 589, and the interference pattern is observed. So similar to what we had before, actually the same. I have a double slit, my screen over here, I get an interference pattern. So I get a really bright spot in the middle, and dimmer spots as I go along. So really bright spot in the middle, followed by a dark spot, followed by bright spots, like that. It looks like that if you were to do it on a wall. I want to know the difference in path lengths from each of the slits to the location of the third order bright fringe. So I'm looking at the third order, that's this one, m equal 3, and I want to know the difference in path length from here to there, and then also from here to the same spot. Now, we know that there is a difference in path lengths because we observed this interference pattern. As we talked about in class, that difference in path length is this distance right here, all right? And that distance, that difference in path length, is d sine theta, all right? But in this case, we don't know theta right off, but I know that d sine theta, in order to give me a third order fringe, is equal to m lambda. So for part A, I just say my difference in path length is equal to m times lambda. That's going to be 3 times 589 times 10 to the minus 9 meters. So the difference in path length is 1.77 times 10 to the minus 6 meters. So one light ray travels that distance further than the other light ray. This bottom light ray travels that distance further than the top light ray. And then what is the distance on the screen from the central bright fringe to the third order bright fringe? Well, this is similar to that first problem. We first want to find theta. It's the inverse sine of m lambda over d, which is the inverse sine of 3 times 589 divided by d, which is 0.1 times 10 to the minus 3 meters. That's given up here in millimeters, but you have to convert it to meters. And that gives me an angle of 1.01 degrees. By the way, you could do this a lot easier because I know what d sine... Oh, never mind. No, never mind. This is the easiest way to do it. And then I want to know what is the distance on the screen. So what is this distance y? Alright, so just like we did before, y is equal to L tan theta. That's equal to 4 meters right here times tan of 1 degree, which is 0.071 meters, which is also 7.1 centimeters. Number 2. Helium neon laser, 632.8 nanometers, sent through a 0.3 millimeter wide single slit. What is the width of the central maximum on a screen 1 meter from the slit? So these work out very similarly. Except I have a single slit instead of a double slit. So when light impinges upon it, it's going to create a diffraction pattern that looks basically the same as the double slit. And I want to know the distance from here to here. I want to know what is the width of that central maximum. Now, I'm going to say that this is a distance 2y because the distance from here to here is going to be a distance y. And I'm going to solve first for y, and then to find the width of the central maximum, then I will find 2y. So I can find this angle theta, and I know for a single slit that the dark fringes are given by this, a sine theta equals m lambda. And this is for the dark fringes. It's a single slit, so this gives the dark fringes. And the geometry here is a little bit more complicated than with a double slit, so we didn't really get into that. But the dark fringes are given by this expression, so I just solve for theta. I have everything that I need. The inverse sine of m lambda over a. Here a, of course, is the width of the slit. So that is the inverse sine of m is going to be 1 times lambda, 632.8, divided by a, which is 0.3 millimeters, or 0.3 times 10 to the minus 3 meters. So that gives me my angle, which is going to be 0.121 degrees. And then I solve for y, similar way as I did before. Y equals L tan theta. The screen is 1 meter away, times the tan of 0.121. That gives me 0.00211 meters, which 2y, twice that, is going to be 0.00422 meters, which is 4.22 millimeters. So that's the width of my central bright fringe. And one other thing, when we're using the single slit diffraction pattern, our order numbers are a little bit different. Our order numbers refer to the dark fringes, not the bright fringes as they do for the double slit. Number 4, light of wavelength 600 nanometers falls on a 0.40 millimeter wide slit, forms a diffraction pattern on a screen 1.5 meters away. So lambda 600 nanometers. This is a single slit, so I'll call the width of the slit A, 0.4 times 10 to the minus 3 meters. And L, the distance to the screen, is 1.5 meters. Find the position of the first dark band on each side of the central maximum, and find the width of the central maximum. This is basically exactly the same as the previous problem. I say A sine theta equals m lambda, solve for theta. M is equal to 1. Lambda is 600 times 10 to the minus 9 divided by A, which is 0.4. Gives me an angle of 0.0859 degrees. Let's draw this right quick. So this angle is the angle to here. That's my angle theta. This is m equal 1 for the first dark fringe. And then I also want to find out what is y. That is, what is this distance, y. Y is equal to L tan theta. L is 1.5, tangent of 0.0859. That gives me 2.25 times 10 to the minus 3 meters, which is 2.25 millimeters. And then the width of the central fringe, that is 2y, is the width of the central fringe. That's 4.50 millimeters. So that's part B, and this is part A. Three discrete spectral lines occur at these angles. The first order spectrum of a diffraction grating spectrometer. If the grating has 3,600 slits per centimeter, what are the wavelengths of the light? At what angles are these lines found in the second order spectrum? So, diffraction grating is a lot like a single slit, or a double slit rather, except instead of just having two slits, you have a lot of slits. Okay, so we have our diffraction grating on the left, and then our screen on the right. And then we get a pattern that develops on the screen that looks a lot like it does with the double slit. So let me draw this. However, within each order, the light of different colors is going to have different angles. So, for example, with the in the first order right here, I'm going to have red light. I'm going to have my red fringe. And then I'll have the other colors, you know, red, orange, yellow, blue. So I'll have different colors within each fringe. And then in the second order, I'll have my colors spread apart. And I'll have these lines spread all throughout. So I'll have this red, I'll have red here, blue, and blue. Now what this is saying is that these spectral lines occurred in the first order. So those spectral lines occurred here. So they had angles of 10.1, 13.7. Their angles were measured like that, but they were still m equal 1. So they all three occurred in the first order spectrum, but because they were different wavelengths, they were refracted, or they were bent at different, well, refracted isn't really the right way to think about it, but their angles were different. Okay? So, in part A, my grating has 3,660 slits per centimeter. I want to first convert that into a distance between slits, so that's going to be 1 over 3,660, which is 2.73 times 10 to the minus 4. That's going to be centimeters per slit if you just invert these units. But I want that in meters, so it's going to be 2.73 times 10 to the minus 6 meters. So that's a few microns apart. Those slits are a few microns apart. And then in part A, I just want to know what are the wavelengths of the light. So I know that d sine theta equals m lambda, and I want to solve for lambda. So lambda is d sine theta over m. All right, I'm going to do lambda 1 first. That's going to be 2.73 times 10 to the minus 6 meters times the sine of 10.1 degrees. That's this first angle right here, divided by my order number, which is 1. And that gives me a wavelength of 478 nanometers. All right, so the 478 nanometers is this one, and it has the smaller of the angles. And then I can do lambda 2, and it's equal to d sine theta over m, which is going to be 2.73 times 10 to the minus 6 meters, sine of 13.7, my next angle, divided by 1. And then that's going to give me a wavelength of 647 nanometers, which is the wavelength of this spot on the spectrum. Still in the first order, but at a different angle, all right, because the light is being spread out into its different colors. And then the third one, I'll just give you the answer here, but it works out the same way. It's going to be 2.73 times 10 to the minus 6 times the sine of 14.8, which is my third angle, and it gives me a wavelength of 697 nanometers. So you would have a third fringe. I see you can't really see it, but you'd have a third color to that spectrum in the first order. Now, it also wants to know in part B, what angles are these lines found in the second order spectrum? So what are these for m equal 2? What are the angles for these guys, here and here, the second order spectrum? And in the lab, when we do a spectrum with a diffraction grating, we'll see the different orders. Okay, so we want to know what is the second order spectrum. I know that theta is the inverse sine of m lambda over d. All right, so for theta 1, it's going to be the inverse sine of 2. That's my m value. Lambda is 478 times 10 to the minus 9, divided by d, which is 2.73 times 10 to the minus 6. And that gives me my angle for theta 1 is 20.5 degrees. And I'm just going to give you values for theta 2 is 28.3 degrees. And then theta 3 is 30.7 degrees. Right, so those are the answers. That's theta 1. Actually, let me go ahead and write out theta 2, just in case you're not clear on this. So I'll write it over here on the left. So theta 2 is equal to the inverse sine of 2 times 647 times 10 to the minus 9 meters, divided by 2.73 times 10 to the minus 6. And so theta 2 is equal to 28.3 degrees. And theta 3 697 nanometer times 10 to the minus 9, divided by 2.73, and then that's equal to what did I say, 30.7. So that's where those numbers come from. That's the second order. And then you can also calculate it for the third order, for the fourth order, until the orders just go away, when the angle at C is 90 degrees. Which brings us to this next one. Okay, number 6 has a grating with 1,500 slits per centimeter is illuminated with a light of wavelength of 500 nanometers. What is the highest order number that can be observed with this grating? Alright, so when we have a diffraction grating, has a bunch of slits in it, creates fraction pattern like we've seen. This is our angle theta. You can imagine that when this angle theta goes to 90 degrees, that you're no longer going to see those orders on the screen just because they go out to infinity. So we no longer see orders when theta exceeds 90 degrees. In practice, you don't see orders in practice well before 90 degrees. But if you have a good enough detector, you should be able to see them out to 90 degrees. So our criterion is going to be theta equal to 90 degrees. And so our first step, we need to find out what D is. It's 1 over 1500. That's this value, the slit spacing. And that gives me 6.67 times 10 to the minus 4. That's centimeters per slit, which is 6.67 times 10 to the minus 6 meters. And then I can say D sine theta is equal to m times lambda. I want to know what is m. As I said, we let theta equal 90 degrees, and the sine of 90 is 1, so this is going to be d over lambda, which is 6.67 times 10 to the minus 6 meters over lambda, which is 500, 10 to the minus 9 meters, which gives me 13.3. That means that you see 13 orders. So I see 13, 1, 2, 3, on up to 13. And then repeat for a grading with 15,000 slits. D is 1 over 15,000, which is 8.89. And then m is equal to d over lambda, which I get 17.8. So with the greater slit spacing, I see 17 orders. 13 and 17.